Long back, we saw that there were two important ways to represent a vector space, as the solution set of a homogeneous linear system and as the span of some vectors. Equivalently, putting it in terms of matrices, you can represent a vector space as the null space of a matrix or as the row space of some other matrix. We've seen that each representation has its uses, so it's important to ask if we've specified a line through the origin in R3 by giving a couple of equations, how can we find a vector that generates the line? If we've specified a plane through the origin as the set of linear combinations of a couple of vectors, how can we find the equation for the plane? The same questions can be asked more generally about affine spaces. How can we go from the representation of an affine space as the solution set of a linear system to its representation as the affine hull of some vectors, or from its representation as the affine hull of some vectors to its representation as the solution set of a linear system? If we can do conversions in the vector space case, the homogeneous case, we can do conversions in the affine space case, the inhomogeneous case. As we've seen before, we can translate inhomogeneous problems into homogeneous problems, solve them, and translate the solutions back. I'll illustrate one such conversion from the representation of an affine space as the solution set of a linear system to its representation as the affine hull of some vectors. We start with a linear system, ax equal b. Let's assume this linear system has at least one solution. Our goal is to find vectors whose affine hull is the solution set of the linear system. I'll illustrate the process with this example linear system. First, find one solution u to the linear system. Here's our solution for this example system. I haven't told you how we can find such a solution. We'll describe a couple of methods in the coming weeks. Next, consider the corresponding homogeneous system. This is the system obtained by just setting these right-hand sides to 0. We know that the solution set of the homogeneous linear system is just the null space of this matrix A and is a vector space, big V. Suppose we manage to find generators, B1 through BK, for big V. In our example system, the null space of the matrix A is generated by the set consisting of a single vector, B1. We can then infer that the solution set of the original linear system is the affine hull of the vectors u, b1 plus u, b2 plus u, and so on up to bk plus u. In our example, the solution set is the affine hull of u and b1 plus u. I'll go through that example again. One solution to this matrix vector equation is this. Now, the null space of this matrix is the span of the set consisting just of the vector b1. So in this plot, the line is the null space of the matrix, and you can see it's generated by this vector b1. The solution set to the original system is obtained by translating this line, by adding the vector u to each of the vectors making up the line. That is, the solution set is u plus the span of the set consisting of b1. That's just the line through the two vectors u and u plus b1. So it can also be written as the affine hull of u and u plus b1. So let's return to the two representations of vector spaces. One representation is as the solution set to the homogeneous linear system a1.x equals 0 through am.x equals 0, or equivalently as the null space of a matrix whose rows are a1 through am. The second representation is as span of vectors b1 through bk, or equivalently as the row space of the matrix whose rows are b1 through bk. How do we convert between one representation and another? So there are two conversion problems. One from left to right. takes as input the homogeneous linear system and outputs generators for the solution set. The other, from right to left, takes the generators and produces a homogeneous linear system whose solution set equals the span of those generators. Let's focus on the first conversion problem, finding generators for the solution set of a homogeneous linear system given by vectors a1 through am. The solution set of this homogeneous linear system is the set of vectors u such that a1.u equals 0 and so on up to am.u equals 0. We can write the homogeneous linear system as a matrix vector equation where the right-hand sides are all 0. The matrix A has as its rows the vectors a1 through am. So finding generators for the solution set is equivalent to finding generators for the null space of the matrix whose rows are a1 through am. Suppose we had an algorithm for this problem. Let's call it algorithm X. The input to algorithm X is the rows of a matrix A, and the output is the set of generators for the null space of that matrix. In fact, later in the course, we'll see several algorithms that can play that role. Now, if U is a vector in the null space, that is, if U has a zero dot product with every row, then U also has a zero dot product with every linear combination of the rows. This motivates a new concept, the annihilator of a vector space. For a vector space big V, the annihilator of big V is the set of vectors U such that U has a zero dot product with every vector in big V. The annihilator of big V is written as big V with an O as a superscript. For example, the annihilator of the span of vectors a1 through am is the set of vectors having zero dot product with every linear combination of a1 through am, which is just the set of vectors having zero dot product with a1 through am, which is the solution set of the homogeneous linear system a1.x equals 0 through am.x equals 0, which is the null space of the matrix with rows a1 through am. So we can interpret our mysterious algorithm X as an algorithm that, given generators for a vector space big V, outputs generators for the annihilator of big V. Let's see some concrete examples of the annihilator. First, an example over the real numbers. Let big V be the span of these two vectors. Then I claim that the annihilator of big V is the span of the set consisting just of 1, 0, minus 1. First, note that 1, 0, minus 1 has a zero dot product with each of these two vectors. Therefore, 1, 0, minus 1 has a zero dot product with every vector in the span of those two vectors. Also, any scalar multiple of 1, 0, minus 1 has a zero dot product with every such vector. We've shown that every scalar multiple of 1, 0, minus 1 lies in the annihilator of big V. But perhaps the annihilator of big V contains other vectors than those in the span of 1, 0, minus 1? No. Every vector with a zero dot product with all of big V must be a scalar multiple of 1, 0, minus 1. So that tells us that the annihilator is exactly the span of 1, 0, minus 1. Now an example over G of 2. Let big V be the span of these two vectors. Then I claim the annihilator of big V is the span of the set consisting just of the vector 1, 0, 1. Note that over G of 2, 1, 0, 1 has a zero dot product with each of these two vectors. So it has a zero dot product with every vector in the span of these two vectors. Now, what other vectors have a zero dot product with all the generators of big V? Well, the zero vector has a zero dot product with those vectors, but that's it. Those are the only two vectors, and that shows that this is really the annihilator of big V. Observe something about these two examples. In the first case, we were working with vectors with 3 entries, and the dimension of big V plus the dimension of the annihilator of big V equals 3. In the second example as well, we were working with vectors with 3 entries, and again, the dimension of big V plus the dimension of the annihilator of big V equaled 3. Here's one more example, using vectors with 4 entries. Big V is the span of these two vectors, and the annihilator of big V is the span of these two vectors. In this case, the dimension of big V plus the dimension of the annihilator of big V equaled 4. In general, if we have vectors with n entries, the dimension of the vector space plus the dimension of the annihilator of the vector space equals n. The proof is simple, given what we already know. Let A1 through AM be generators for big V, and let A be the matrix whose rows are A1 through AM. Then the annihilator of big V is just the null space of the matrix A. The rank nullity theorem states that the rank of A plus the nullity of A equals n. Well, the rank of A is the dimension of big V, and the nullity of A is the dimension of the annihilator of big V. So the theorem is true. Now that we know a little about the annihilator, let's return to thinking about converting between representations of a vector space. We originally said that our algorithm X takes as input the rows of a matrix A and outputs generators for the null space of A. But we can equally well interpret algorithm X as an algorithm that takes as input generators for a vector space big V and outputs generators for the annihilator of big V. As we've said before, the conversion problem in which we go from a homogeneous linear system to generators for its solution set is solved by this algorithm X. But what about the other conversion problem? I've interpreted the left to right conversion as given generators for the vector space big V, output generators for their annihilator of big V. Accordingly, I'm going to interpret the reverse conversion problem as given generators for the annihilator of big V, come up with generators for big V itself. Maybe we could hope for a mysterious algorithm Y to solve this conversion problem. Well, crazy idea, but what would happen if we applied algorithm X to the generators for the annihilator of big V? Well, we know what would happen. You feed in the generators for the annihilator of big V to algorithm X, and it'll find you generators for the annihilator of big V. What good will that do? It turns out this is exactly what we want, since as we will show, the annihilator of big V equals big V itself. This tells us that when we are given generators for the annihilator of a vector space big V, and we want to get back generators of big V itself, we can just use algorithm X. We still have to prove this theorem. So here we go. Theorem: the annihilator of big V is big V itself. Here's the proof. Let A1 through AM be a basis for big V, and let B1 through BK be a basis for the annihilator of big V. Since B1 is in the annihilator, it has a zero dot product with every vector in big V. So in particular, it has a zero dot product with the basis vectors A1 through AM. Similarly, each vector BI of the basis of the annihilator has a zero dot product with A1 through AM. Now, since A1 has a zero dot product with B1 through BK, it follows that A1 has a zero dot product with every vector in the span of B1 through BK. We choose B1 through BK to be a basis for the annihilator of big V. So we see that A1 has a zero dot product with every vector in the annihilator of big V. This shows that A1 is in the annihilator of big V. Similarly, A2 is in the annihilator of big V, and so on. Therefore, every vector in the span of A1 through AM is in the annihilator of big V. Thus, the span of A1 through AM is a subspace of the annihilator of big V. But that span is just big V itself. So big V itself is a subspace of the annihilator of big V. We're almost there. We've shown that big V is a subspace of the annihilator. To show it is equal, by the dimension lemma, we only need to show that the dimension of big V equals the dimension of the annihilator. Suppose we are working with vectors having n entries. Let's apply the annihilator dimension theorem to big V. It tells us that the dimension of big V plus the dimension of the annihilator of big V equals n. Now let's apply the annihilator dimension theorem to the annihilator of big V. It tells us that the dimension of the annihilator of big V plus the dimension of the annihilator of big V equals n. Together, these equations show that the dimension of big V equals the dimension of the annihilator of big V. And that completes the proof.